something called electron configurations. And what we're going to do is deepen our understanding of what's going on with electrons. We've been running with the Bohr model. Turns out the Bohr model has some flaws. It's good, it helps in some ways, but now we're going to try to understand what electrons are really doing. So we're going to talk about something called electron configurations. Now, maybe someday when I'm here, we'll talk more about Schrodinger's cat and these videos. But I think for today, we're just going to concentrate on um, developing an understanding of these electron configurations. So you should have a note sheet that goes along with this. This guy, Werner Heisenberg, if you've ever seen Breaking Bad, the main character in Breaking Bad named himself after those, but he developed the uncertainty principle. And what he said was it's impossible to know both the position and momentum of an electron at the same time. So, in other words, we can kind of know a little bit about how an electron's moving, but then we know less about where it is exactly, and vice versa. And long story short, it's impossible to pin down exactly where electrons are. So, he said there's this thing called atomic orbitals, and orbitals are areas with a 90% chance of finding an electron. So, we're going to add some more details to the Bohr model, as I said. So, everything I'm going to be talking about here is just ways of talking about where an electron is. And it's sort of like I could talk about where you are. You know, you're in the United States, you're in the state of Colorado, you're in the city of Aurora. You're at Cherokee Trail High School, and we could get down to the actual room number and seat you're sitting in. So I could be more and more specific about where you're actually located. With electrons, it's similar. The biggest category is what's called primary energy levels. And with Bohr models, that's kind of where we left it. We ignored all the additional details. But you can also take primary energy levels and divide them into sublevels. And then sublevels can be divided into orbitals. And importantly, an orbital is a thing, an area where two electrons can be. So of all orbitals hold a maximum of two electrons. And as I said, we ignored the presence of sublevels in Bohr models. So I'm going to break this down for you. It's going to seem kind of crazy at first. I think there's some spots on your notes for you to fill this in. But we're going to learn that we can look at the periodic table, and it can really tell us a lot of this stuff. So the first primary energy level, which again is kind of like the ring on the Bohr model, only has an S sublevel. It's the smallest one. And as we already know from Bohr models, the first energy level can only hold two electrons. The second primary energy level has what are called S and P sublevels. The third has SP and D, and 4 and above have SP, D, and F. And again, this will kind of make more sense when we do some examples and see how this works with the periodic table. Now, sublevels can be divided into or contain a certain number of orbitals. So the S sublevel has one orbital, and so two electrons can fit in an S sublevel. The P sublevel has three orbitals and a maximum of 6 electrons in that entire sublevel. D holds 5 and a maximum of 10 electrons, and F has 7 orbitals and therefore holds 14. So notice the number of orbitals is always half the maximum number of electrons because there's always 2 electrons per orbital. So when I take the number of orbitals and I multiply it by 2, I can figure out how many electrons can fit in that sublevel. And again, this will make more sense when we see how this all fits together and works with the periodic table. So this is Schrodinger who developed these orbitals, and we don't need to know what they look like, but basically he came up with some really fancy math equations that these are the shapes of all these different orbitals, basically. And again, you don't need to know these, but again, we can see there's a single S sublevel, 3 P sublevels, 5 Ds, and 7 Fs. So in a minute, we're going to be writing something called electron configurations. And I think there's some space on your notes to write this in. And I would very highly recommend that you do so. When we're writing these electron configurations, as you'll see in a second, you're going to want to know what all these things mean. So the first big number is the primary energy level of the electrons. And again, this is equivalent to the rings on the Bohr model when we were doing that. But now we know there's some additional stuff. There's a sublevel, which can be S, P, D, or F, in this case P. And then this superscript is the number of electrons in that sublevel. So it's just, again, it's a way of talking about where electrons are. So these electrons, in this example, they're in the fourth energy level, or the fourth ring of the Bohr model. They're in the P sublevel, and there are 5 electrons in that sublevel. So when we're writing these things in a second, this is going to give you a better idea of what all this stuff is. So go to the next slide here. Okay, so if you haven't already, you're going to need to get out your periodic table, and we probably have already added these letters and numbers to the periodic table. And but I want to point out some other things. We didn't write this S, D, P, and F block, at least the year that I recorded this. So this is known as the S block right here. This is known as the D block. This is known as the P block. And a moment ago, when we were talking, we said that the S sublevel holds a maximum of 2 electrons. And if we kind of ignore this little part here, because that's the weird part, you'll notice there's 2 boxes in this area. So that corresponds to what I said earlier. The S sublevel holds 2 electrons, and then we can also, again, notice that there's 2 boxes in this area. Maybe it'll help if I have my laser pointer on. Here is the P block. So this little kind of area right here, see that? I said a moment ago, you can fit a maximum of 6 electrons in a P sublevel. There is also 1, 2, 3, 4, 5, 6 boxes here. I said there is 10 electrons that can fit in a D sublevel. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then again, the F block holds 14, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So all that stuff I was saying earlier about the sublevel and how many electrons fit in them, you can be reminded about all that stuff by just looking at the periodic table here and counting the boxes. Another example would be, so I said the D sublevel contains a maximum of 10 electrons, and we counted 10 here. If I want to know how many D orbitals there are, I just divide that by 2, which would be 5. In the P sublevel, there is 6 boxes. Divide that by 2. There's 3p orbitals. There's 3 orbitals in the P sublevel, I should say. So if you want to know how many electrons fit in any sublevel, count the number of electrons in that block, count the number of boxes in that block. That's the same as the number of electrons. Divided by 2, that's the same as the number of orbitals. So let's actually put this into practice and write something that's called electron configurations. And what this is we're going to sort of just kind of map out where all the electrons are. And here's a list. I would suggest, I think there's space in your notes for you to write these in as we do them. But let's look at lithium first. And don't overthink this. It's easier than it seems at first. We're literally just counting boxes and writing down what we see and stopping when we get to the element in question. So I'll show you what I mean. I'm going to turn on my pen here. So lithium, we're going to write what's called an electron configuration for lithium. It's right here. So when I see one of these, I see a 1s, I'm going to write down a 1s. So when you see one of those, write it down. And I'm just going to move across the periodic table left to right and down and count boxes till I get to the one I'm trying to do, which is lithium in this case. And that's when I'll stop. Every time you see one of these, write it down and count the number of boxes till the next one. So 1s, 1s1, 2, so I count 2 boxes, but I'm going to stop counting because then I encounter a 2s. So because I counted 2 before I got to 2s, I'm going to write a 2 there. And then I'm going to write down 2s because I see a 2s. and then I see a 1, and that's it. That's lithium's electron configuration. 1s2, 2 boxes there, 2s1. Notice these superscripts here, 2 plus 1, 3, add up to the total number of electrons that lithium has, which is 3. Let's do another example. Let's do silicon. Okay, so silicon's right there. I'll put a little dot on it. I'm going to count, literally just count the boxes till I get to silicon. Every time I see one of these things that we wrote down, I'm going to write it down and record the number of boxes till I see the next one. So again, 1s, I see a 1s, I write down a 1s. I count a box. There's 1 box. There's 2 boxes. I'm going to stop counting because I got to a 2s. So I'm going to go 1s2. I'm going to write down the 2s because I saw 2s. 1, 2. I'm at beryllium now, but I'm going to stop counting. I'm going to put a 2 there. I'm going to stop counting because I ran into the 2p. 2p, 1, 2, 3, 4, 5, 6. But I'm going to stop counting because I ran into 3s there. 3s. 1, 2. I stopped counting because I ran into 3p. 3p, 3p1, 3p2. There's silicon. I stopped counting, so it's 3p2. And again, these subscripts here would add up to the total number of electrons silicon has. So 2 plus 2 plus 6 is 10, 12, 13, 14. That is how many electrons silicon has. So I know this can seem really weird at first to some people, but I'm literally just counting boxes and writing these little numbers and letters down as I see them. Let's do another example, titanium. So titanium's element 22. It's right here. I'll put a little red dot on it. Okay, back to the top. And by the way, these will always start off the same way. So the first thing I see at the very top is 1s, 1s, and I'm going to count 2 boxes. 1, 2. I'm going to stop counting because I run into 2s. So I counted 2 boxes before I ran into 2s, so I put a superscript 2 there. 2s1, 2s2. Stop counting because I run into 2p. So I'm going to write down that 2p. 1, 2, 3, 4, 5, 6. Stop counting because I want to run into the 3s over there. Let's write down that 3s. 3s1, 3s2. Stop counting because I'm going to run into 3p. So I'm right here right now at aluminum. 3p1, 2, 3, 4, 5, 6. 3p6. Stop counting because I ran into 4s. 4s1, 4s2. Now let's be careful right here. So 4s2, I'm right here at calcium. I'm going to write that down. And then we notice what comes next is 3D. That is correct. I'm going to write it down here a little bit because I'm running out of room. 3D, and then 1 at scandium, 2 at titanium. So that is titanium's electron configuration. And yeah, we got to watch that transition. It goes from 4s to 3D. Basically, it has to do with the order in which electrons are going to fill these orbitals. So these electrons do go back to the 3rd energy level after the 4s. And for now, maybe just take it for granted that that's what happens. All right. Another example, gallium. It's kind of blocked by my 4p here, but it's right there, element 31. So back up to the top. Again, these are going to start off the same. There is a shortcut we can talk about in a second. But it goes 1s2 because I got the 1s there. And I count the 2 boxes. What do we see next? We see 2s2. Again, this is going to be exactly the same as the titanium until the end. We have 2 there. And then next comes 2p, and there's going to be 6 boxes there. 1, 2, 3, 4, 5, 6. What do I see now? I see 3s. I see 2 because there's 3s and there's 2 boxes until I run into 3p. 3p, there's going to be 6 there. And that gets me to where argon is. What do I see next? I see 4s. I see 2. I'm stopping at 2 because 3D comes right there. And Now here we're going to go past titanium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3D 10. And then, so I'm right here at zinc. Gallium's right here. So then it goes to, right down here, 4p1. 4p1. Okay. So manganese. Why don't you take a second and maybe we could pause the video and let's see if we can get manganese. Manganese. And yeah, also molybdenum. We can do that one too if you haven't already. So we can pause and do molybdenum. So here's the electron configurations. Manganese 1s2, 2s2, 2p6, 3s2, 3b6, 4s2, 3d5, and molybdenum, maybe just to go over that one, 1s2, 2s2, 2p6 gets us to right here, 3s2, 3p6 gets us to argon, 4s2, 3d10 goes to zinc, zinc, 4p6, and then it goes down here to 5s2, 4d, 1, 2, 3, 4. And that's how that ends up. So as we can see, that gets a little bit repetitive, and especially if you can imagine writing one way down the periodic table, it would take a long time. So you need to know how to write full electron configurations, which you've just been doing, but if the question says so, you can use the noble gas shortcut. And what you do is you write the noble gas at the end of the row prior to the given element in brackets, and you continue from there. And this only works with noble gas is the only thing you can use. You don't use any other spot on the periodic table, and I'll show you what I mean. So potassium, zirconium, bromine, and barium. Okay, so doing the noble gas shortcut for potassium. So first of all, we find potassium, element 19. And then we remember, of course, that the noble gases are these things over here. Okay, group 18, these guys over here. So these are the ones we use. So potassium, what I want to do is go to the noble gas in the row above the one that I'm trying to do. So potassium is in period 4, so I go to the end of the row above, which is argon. And so what I'm going to do is I'm going to write argon in brackets like that. And basically that saves me from having to write everything up to argon, and then I just continue from there. So it's like that. It's obviously much easier and much faster. And, there's a real repetitive nature to these electron configurations, as you saw. So this sort of prevents you from having to do all of that. And so for potassium, we would just do that. And again, this is if if the question says you can do the noble gas shortcut or should do the noble gas shortcut, that's the way you do it. Zirconium, element 40. Okay, so it's in period 5, row 5. I'm going to go to the noble gas at the end of the row before, which is krypton, element 36. So I write krypton in brackets, and then I can just continue from krypton, which after krypton, we get to 5s2, and then we go to 4d2, because there's zirconium right there. So again, quite a bit easier, quite a bit less writing to do. Let's look at another example of bromine. So first of all, find bromine, which is right there, element 35. Go to the row above, go to the noble gas, that's in the row above, it's argon again this time. And then again, I can just continue from argon. 4s2, 3d10, 4p5 will get me to bromine. Barium, I guess I'll just do it. Barium, we got xenon, Xe, because barium's, here's xenon right here. Barium is element 56, so the noble gas right below that is barium. And then we're going to go 6s2. And just there they are again. There are some rules about how electrons fill orbitals. These are going to make more sense when we see some examples, but you have them here in your notes. I just want to have you get the terminology here, and then we'll kind of talk about how this applied a little bit later. But basically, this is if you had an atom and you sort of removed all the electrons from them and you started dropping them in, this is how they would fill up. So something called the Aufbau principle says electrons are going to fill the lowest energy orbitals first. And that's going to be the highest priority rule. The Pauli exclusion principle says only 2 electrons fit in each orbital and they have opposite spins. You can think of it as just an electron as a little ball, and if there's 2 electrons per orbital, one is going to spin one way and one is going to spin the opposite way. It's not actually what's happening, but that's a way you can think of it. That's fine. And then there's something called the Hund's rule, which is the bus rule, which electrons enter orbitals one at a time until they must double up. And again, I'm just throwing some terminology out there. Doesn't really make a lot of sense until we do something called orbital diagrams that are going to go along with this. And I'll explain all these further in a different video when we look at some of these examples. But I just wanted to throw out this terminology just so you have it in the notes, and then we'll go back and look at it later. Yeah, this is kind of a map, but let's talk about valence electrons, which we have talked about before. But these are all of the electrons in the highest or outermost energy level of an atom. This can include electrons from different sublevels. So, for example, if we did fluorine's electron configuration, it is 1s2, 2s2, 2p5. And we could ask ourselves, how many valence electrons does this have? So I want to remind you of a couple of things. This number in front is the primary energy level that the electrons are in. So these 2 electrons right here are in the first energy level, and these electrons are in the second energy level, as are these. So remember, this number in front is basically just like the ring of the Bohr model that we were drawing. So all of these that I'm now boxing in red are in the second energy level, and so the total number of valence electrons is 7. These 2, maybe I should erase this now. Oh, can't erase it. Okay. There we go. So the ones I have in red, this is both of these, all the red ones are in the second primary energy level. So 2 in the S and 5 in the P, and that's 7. And that's the same thing we would have gotten if we had drawn fluorine's Bohr model. Another example is selenium and how many valence electrons. So I have argon's, or I have the noble gas shortcut for selenium's electron configuration. And it says how many valence electrons. So this is a little tricky. Notice how there's a 4s, and then it goes back to 3d, and it goes back to 4p. So again, the big number in front is the primary energy level that these electrons are in. The valence electrons are all of the electrons in the highest or largest beginning number of the energy levels. So the highest beginning number that I see is a 4. That's smaller than 4. It's a 3. So the valence electrons are these 2, which is 2, and these 4. 2 plus 4 is 6. So selenium has 6 valence electrons. These 2 from the 4 and then these two from the 4s and these two from the 4p. Now, luckily, there's a way in the periodic table to see very quickly how many valence electrons things have, but that's a way to look at it from the noble gas, from the electron configuration, I guess. But there's another easy way we'll talk about later to figure it out from the periodic table. Kind of like when we did Bohr models, we drew Bohr models of neutral things and we drew Bohr models of things with a charge. You can do the same thing with electron configurations. As we kind of talked a little bit about, full valence shells, or especially full S and P sublevels, are particularly stable, not in a radioactivity type way, I mean in a chemical reaction type way. So the noble gases, if you look at their electron configurations, they have completely full S and P sublevels. They always end in, like, for example, 2s2, 2p6, or in all cases, the S and P sublevels are completely full with noble gases, and they are very stable and non-reactive, really, for that reason. We just happen to live in a world where that pattern of electrons is really stable. So what atoms will do, and we'll talk in a bunch more detail about this in the next unit, is they will do things to get a stable configuration, mainly become ions. And they will get electron configurations that are similar to or exactly match the electron configuration of a noble gas. Now, I want to make it very clear they're not turning into a noble gas, but they will get a pattern of electrons similar to a noble gas. So ions have different electron configurations than the atom they came from, just like they would have a different Bohr model than the atom they came from. So you kind of got to write the electron configuration for an ion and then kind of think about what would happen. Is it gaining electrons? Is it losing electrons? Make an adjustment and then go from there. So, for example, if I was going to write the electron configuration for Na plus 1, the first thing I should probably kind of think about is what would just normal old NA's electron configuration be? Let's just go ahead and write that real quick. 1s2, 2s2, 2p6, and then 3s1. Now again, this is regular sodium's electron configuration, but I want Na plus 1. How do I get an eraser? Well, the bottom line is it's plus 1, so it's going to lose 1 electron. So the 1 electron it's going to lose is these 3s1s right here. And then it's going to have this. This is going to be the electron configuration that I'm writing in a box of Na plus 1. And notice that it exactly matches neon's electron configuration. And so for the ones that we're going to do, at least, the electron configuration of ions is always going to match that of a certain noble gas. Let's look at another example. Okay, so sulfur minus 2. So let's kind of start writing this. Here's sulfur. So regular sulfur would be 1s2, 2s2, 2p6, and then 3s2. Okay, so we're coming up to sulfur here. Normal sulfur would end in 3p1, 2, 3, 4. That's what normal sulfur would end in. But sulfur minus 2 has 2 additional electrons. It has 18 instead of 16. So instead of going 1 box less, like I did with Na+, I'm going to go 2 boxes more, and I'm going to end in 3p6. And again, we notice this matches this electron pattern from one of the noble gases. And as always, if you add up these superscripts, it adds up to the number of electrons. So 6 plus 2 is 8. And then we add another 6 to that, which is 14, 15, 16, 17, 18, which is how many electrons sulfur minus 2 has, 18. Okay, so hopefully that gets you a start. Hopefully that makes some sense. I'm going to stop this video for now, and you enjoy the rest of your day, all right?